Jai Hind everyone. So myself Ritesh Kumar Sharma. I am from Ajay Kumar Garg Engineering College, Ghaziabad. So my subject is Fundamental of Electrical Engineering, which is taught in the first year. The code of the subject is BEE 101 in first semester and it is 201 in second semester. So today I am going to take the topic of efficiency of single phase transformer, which is a part of the unit number 3. So in efficiency of single phase transformer, we all know that in a single phase transformer, the efficiency is a very important factor for the performance of the transformer. Okay, so in the previous lectures, we discussed about the transformer, the working of the transformer at no load and at load, and then the equivalent circuit of the transformer. Now today we will discuss about the efficiency of the single phase transformer. So as you can see that we all know that the efficiency of the transformer is defined as the ratio of output power to the input power. So output power and the input power. So here you can see that the output power and input, the input means what? The input you can see that the input is given by output plus losses. The transformer has some losses because we are talking in terms of actual transformer, not the ideal transformer where we generally ignore the losses, but here we will consider the losses in a transformer. And in the transformer, the losses are two types of losses. These are the iron loss and copper losses. Iron losses and copper losses. So the iron losses and copper losses. So iron losses are also called the core losses because these losses are generally happen in the core of the transformer, and it is also called iron losses. So basically in our transformer, which when a supply is given to the primary winding of the transformer, the alternating flux is this set up in the transformer core, and because of this flux, which is AC in nature, the hysteresis and eddy current losses takes place in the magnetic core. And this flux is set up in the core remains constant, as the flux in this particular flux is core in the core is constant throughout the operation. So these losses are generally called constant losses. They are also called constant losses. So the core losses are two types, like hysteresis losses and eddy current losses. Let us discuss first more about these core losses. So as I just told you that the hysteresis losses are the losses when the magnetic material is subjected to the reversal of the magnetic. When as we all know that the flux is alternating in nature. So the flux, suppose that if the flux is there, which is alternating in nature, that is phi is equal to phi m sine omega t. And because of this alternating nature of the flux, the magnetization and the demagnetization of the core taking place. And this, because of this, the reversal of the molecule's magnet and it takes some electrical power, which is further dissipated in the form of heat, is known as hysteresis losses. And the formula for the hysteresis losses is pH is equal to KH into Vm to the power 1.6 F into V, where KH is the constant of proportionality, Bm is the maximum flux density, F is frequency, and V is the volume of the core actually. And the major important part is that this loss can be minimized by using the good quality of the core material, like a silicon steel. As I mentioned, we can use this material for the construction of this transformer. Second thing is the eddy current losses. So again, this flux in the core is the transformer is, as we all know that the flux in the core is the transformer is alternating. And because of this alternating nature of this flux, the some induced current in the core of the transformer is taking place. And this induced EMF, because the flux is changing, the volt induces EMF in the core of the transformer, and this induced EMF is responsible for this circulating current in the core of the transformer. And this power is required to maintain this eddy current. Okay, so eddy current is flowing in the transformer, and this power is dissipated in the form of, again, heat is called eddy current losses. So because of this eddy current, the heat loss is taking place, and the formula is given by PE is equal to KE Bm square F square T square, where K is again is the constant of proportionality. Bm is the maximum flux density. As we all know that the flux density is called the flux per unit area, the flux, and it depends upon the area of the core. F square is the frequency square. T square is called the thickness of laminations. So these losses can be minimized by making the core of thin laminations. If we are using the core of thin lamination, then we can minimize, and this T is called the thickness of the lamination. So depending upon the thickness, we can minimize this eddy current losses. So the core losses or the iron losses are basically of two types, called the hysteresis losses and eddy current losses. And since the flux remains the constant in a core, these losses remains constant. Hence, they are called the constant losses. So these are called core losses or iron losses. Next is the copper losses. Copper losses is occurring both, since the transformer has two windings, primary winding and secondary winding, and both these winding has the resistances in actual transformer. So R1 and R2 are the primary and the secondary resistance respectively. Hence, the copper losses is also known as the I square R losses or ohmic losses. The total copper losses is given by I1 square R1 plus I2 square R2. Or you can also write it I1 square R01 and I2 square R02. So this R1 and R01 and R02 is nothing but its equivalent resistance referred to primary side, and the equivalent resistance referred to secondary side respectively. When we refer the resistance in the primary side and secondary side, these are the resistance, because the total resistance remains same whether you are referred to the primary side and secondary side. Its equivalent resistance referred to primary and secondary. Hence, these losses, these I square R losses, are called the copper losses. So it depends upon the current actually. Okay. So our core losses, generally talk about the core losses or iron losses are depend on voltage dependent, because they depend upon the voltage, and since the voltage is constant, the iron losses remains constant. And the copper losses are generally based on the current or the load, you can say, they are also called, and the currents in the load is variable. Because of that, the current will be changing, hence it is called the variable losses. So copper losses are this, and these losses are called the variable losses. So these are something about the losses in a transformer. So losses in a transformer are two types. First is the core losses and iron losses. Now from this we will discuss about the efficiency, the transformer efficiency. The transformer efficiency, I just told you that it's a ratio of output power to the input power, or you can write it like that, the output upon output plus losses, and the losses is iron losses and copper losses. Copper losses, okay, copper losses. So we know that the output of a transformer, in a transformer, we know the output is given by the voltage, current, and the power factor of the load. Suppose that the power factor of the load is cos phi 2. So hence the output power must be equal to V2 into I2 into cos phi 2. It's my output. upon output this plus upon this our iron losses and copper losses. The iron losses is mentioned by Pi and the copper losses by Pc. Here, as I had just mentioned that this iron losses, which is the combination of hysteresis and eddy current losses, and the copper losses, which is indicated by Pc, is called full load copper losses. Full load means when it is working at a rated capacity, when the transformer is working at a rated capacity. So when it works at the rated capacity, the full load current will be flowing in the secondary side of the transformer, and this is given by I square R into Re. Res is the effective resistance secondary side, or you can consider it in primary also. So these are some. V2 is the secondary terminal voltage, I2 is the full load secondary current, and cos phi 2 is the power factor load. So this is the transformer efficiency. So you can calculate the efficiency by simple this formula. Now, if suppose that if the transformer is working at some other load, suppose X is the fraction of the full load, in that case efficiency can be calculated by this method. As you can say that X is nothing but it is the ratio of actual load upon rated load. Suppose that the transformer working at some of the half load, or you can say the 1 by 25% of the full load, 75% of the full load. So depending upon that, you can calculate the value of X. X is nothing but it is a fraction. So if X is a fraction of the full load, the efficiency of the transformer is given by the relation, because since here now the transformer is working at some at a fraction of the power plant, so we can multiply by X to the output of the, or the rated of the your transformer. So that is X into V2 I2 cos phi 2, where V2 I2 cos phi 2 was the rated output, output of the transformer. And as we know that when the load is varying, the iron losses will remain same, but the copper losses will vary according to the current in a transformer. So hence copper losses is proportional to the current. So if the current is I2 square and current is changes according to the your fraction of X, so based on the copper losses is equal to X square into full load copper losses. So obviously copper losses proportional I square losses, and I will be changes as fraction of that, because the voltage remains same at that part. So here the copper losses will be changes like this: X square times of I square, where this is the I square, Rec is the full load copper losses. That is copper losses at full load. You can say like this. So this is how we can calculate the transformer efficiency at any load, 10%, 50%, 75%, and whatever. Because we know that the transformer, the output load is varying. Morning the load is different, in afternoon the load is different, and throughout the 24 hours you can say that the efficiency, you can say that the load in a transformer is variable. So in that case, when the load is variable, the current will be changes accordingly. Load current, obviously. So this is how you can calculate the efficiency of the transformer at any load. Okay. Now, if someone asks that, find the condition for maximum efficiency with this actually. So this is the means at what load the efficiency is maximum. To calculate this condition for maximum efficiency, suppose that we have to find the efficiency. So efficiency is given by the is given by output upon input. So x times of this V2 into I2 cos phi t. Suppose that V2 I2 cos phi t is a P. P is the output. So here x into P upon x into P plus Pi is the iron losses and P copper is the full load copper losses in a transformer. We have assumed that these are copper losses. So suppose we have to calculate the transformer maximum efficiency, condition for maximum efficiency, and when to find the condition for maximum efficiency, we need to differentiate this efficiency with respect to x, because x is a variable here. Because x is nothing but it is changing. Okay, so when we differentiate it with respect to x, this will be equal to your differential of first function, that is p, for second function pi plus x square p copper minus first function and differential of second. When we differentiate with the x, it will be p plus this is a constant, pi is the iron losses, they are constant, hence it is 0, and plus 2x p copper upon the square of denominator, the xp plus pi plus x square p copper square. Okay, and when we equate it to 0, we will get the condition for maximum efficiency. When we equate to 0, we will find that this will become 0 and x p square plus ppi, p into pi plus x square p copper minus x p square minus of 2x square p into p copper equal to 0. Straightforward, this will be cancelled out. Okay, and you will get pi x square p and 2 square will be minus of x square p copper equal to 0. P again we can take and cancel out. So you will get pi is equal to x square p copper. So this expression will tell you, this expression you can see that is called the iron losses is equal to x square p copper, which is the copper losses at any load. So pi is equal to x square p copper, and where p copper is the full load copper losses at rated load. So iron losses is equal to copper losses, So this is the condition for maximum efficiency. At maximum efficiency, the iron loss will be equal to copper losses. So from this expression, the x will be equal to under root of iron losses plus full load copper losses. This is a condition. Okay, and from here, as we all know that x is nothing but it is the ratio of actual load upon rated load. So from there, at maximum efficiency, the load on a transformer we can determine. Okay, so the load at maximum efficiency, since x will be equal to the load at at maximum efficiency divided by rated load on transformer is equal to iron loss upon copper loss. So the rated kVA we can represent in terms of kVA. At maximum efficiency is equal to rated load, rated kVA into iron loss upon copper loss. So from this we can calculate the load on a transformer at maximum efficiency given by this expression. Where Pi is the iron losses and P copper is the full load copper losses on a transformer. Okay, so this is how we can calculate the rated load. So the transformer efficiency can be determined for any load for a single phase transformer, and the maximum efficiency of the transformer can be calculated. Now let us solve one numerical based on the single phase transformer or efficiency of transformer. So I am just solving this problem, and then based on the above concept, that is the efficiency. So the numerical is, or the question is, the iron and the full load copper loss of a 100 kVA 6600 by 400 volt single phase transformer are 600 watt and 900 watt. Okay, so iron losses is given as 600. So in our problem it is given as the iron losses is given as Pi is given as 600 watt, and full load copper losses is given as 900 watt. Okay, so these two losses are given to us. Now it is given that it has to be calculated that the efficiency of full load and half load at 0.8 power factor. So we have to calculate the efficiency at full load and half load at a particular power factor called 0.8 lagging. We have to calculate the load at which the maximum efficiency is obtained and its magnitude at same power factor. So load at maximum efficiency and the maximum efficiency at the same power factor. So first of all, we will calculate the efficiency of a transformer at single phase loading. So you know that at this particular losses, suppose we calculate the efficiency at full load. So at full load means the transformer working at rated load, which is your 100 kilovolt ampere. So 100 kVA. So full load means X is equal to 1. So 110 to the power 3 into the cos phi, which is given as 0.8. This is our output of a transformer because it is working at full load or rated load. So this is the output. So if we apply the formula, that is the V2 I2 cos phi upon V2 I2, the same output is this 100 kVA into power factor is 0.8 plus iron losses Pi, which is given as 600, and P copper, which is given as 900, because we are taking the full load. So full load copper losses are there. So to calculate this, when we calculate this, we found that the efficiency of the transformer will be 98.15%. 98.15% at full load. So full load efficiency is given by this. In a second, let us calculate the efficiency at half load. At half load, the transformer working at half of its rated capacity, half load. The value of X is half. So actual load will be half of the rated. That is something around 50 kVA. So it is 50. That is 100 into 0.5. It is 50. 10 to the power 3. And power factor is same, 0.8. So output, 0.8 plus iron losses. So iron losses will remain same, but the copper losses will be changes since it is a current dependent. So copper losses X square full load copper. X means here it is X, the value of X is half. So 1 by 2 square, half square into full load copper losses, which is given to us 900. So here the copper losses will become X square times, if X is equal to 1 by 2, X square will be 1 upon 4. So when we calculate this, the copper losses will be given by 97.97. So these are the two efficiencies at full load and half load. Now in the next part of our this is we have to calculate the efficiency at calculate the load at which maximum efficiency obtained. So we know that at maximum efficiency just a minute. At maximum efficiency, the value of load is given by the load at so load at maximum efficiency is given by rated load and Pi upon P full load copper. So rated load is given as 100 kVA, iron loss is 600, copper loss is 900. So the rated load will be given as 81.65 kVA. So at this load, this transformer will have the maximum efficiency. Now we will calculate the maximum efficiency. The maximum efficiency is given as the load that is 81.65 kVA. So we have to calculate this efficiency at same power factor, that is 0.8. So at 0.8 power factor, again it is 81. This is the output, plus iron losses 600, and we have to calculate the copper losses also. But at maximum efficiency, both the losses will become same. That is, the copper loss will be equal to iron loss. So this will be, again the copper loss will be 600. So when we calculate this must be equal to your 98.2%. So here you can see that this is the maximum efficiency. You can 98.2. In case of full load, it is 98.15. In case of half load, it is 97.97. So we have seen that in this lecture. So first we have to calculate the losses, we determine the losses, and then we calculate the efficiencies. So this is the efficiency and the losses and efficiency of a transformer at a different load. We can calculate it accordingly. So thank you so much for this. This next we will calculate. We will come with the different topics on the transformer. Thank you so much.